So what I'm going to show you here is a method that's applicable to a number of applications. So as Doug said, horizontal wells is one. I'm actually starting with another example here, which is like a tunnel, which is more from the mining space. To understand where what the issues that we are trying to tackle here is, we look at the following model. It's relatively simple. Well, the model is actually pretty complex, but from the concept here, there is a river or the several surface water features at the top, and then there's a tunnel that's going down here. And this model is pretty complex, of course, so I've simplified this for the next slides. The question here that arrives is when we look at the river and the mine, and when we simplify that on a more conceptual space, then we can see that from the river to the mine we've got a flux. And the question arising here is, during the construction period, how much water do we actually get into the tunnel? So that's the general question here. Similar questions can arise from horizontal wells, for example, or point sources. But now the question is, what is actually important here? So when we think about model sensitivity, uncertainty analysis, there are certainly features in the model or certain areas in the model that are not that important to model at any detail, at any level of details, and some are. So what I'm showing on the next slide is an estimation on the sensitivity of the K value to the influx into the mine. And when we have a look at this, so this is basically for every cell, when I'm changing the K value in any cell, how does it influence the result? So what we can see here is that most of the model is not really sensitive. So if I would change the K value down here, or another way, if I do a mistake in my modeling down here, it has very little consequences. Okay. But what we can clearly see here is that the closer we are getting to the river and the closer we are getting to the mine, the more important it is to be really accurate in what we are modeling there. The more sensitive the model is becoming, right? So, and this is a bit worrying because actually thinking about the tunnel here, the inflow into the tunnel is dominated by very local scale processes. For example, curvilinear flow into the tunnel is very heavily influenced by the size of the tunnel, the geometry of the tunnel, the lining of the tunnel, and so on. So this small scale feature here has the potential, at least, to dominate the whole system. All right. So we have processes on different scales here. We've got a large scale process, like the regional groundwater flow, but we also have small scale features, so how the water is getting out of the river and into the tunnel. And that's worrying because when we look at these two features in here, the river in this model is only expressed by a couple of elements. It's very coarse, it's very rough. We probably have a lot of structural error in this model over here. Same with the tunnel over there. So what we actually would like to do here is, because we know this is very sensitive, we need to have a more accurate model around these areas. So this should maybe look like this. So we have like, well, we have a topography there, we have a clogging layer there with a different K value, and these are all features that can dominate the system because the whole chain, the whole conceptual model is that this resistance is basically in a line with this resistance that we see in here and the resistance over there. Okay, so with finite elements we have a benefit here because we can actually resolve this and we can put this together in the same model. But if I model like a horizontal well like this on regional scale, I'm ending up with millions of elements. We can't do that. Right, so even if I have the possibility for this, what's called explicit modeling, so we are really resolving everything at every detail, that would work, but it's not practical. So we need a solution for that. And the solution we used here is upscaling. So what we are doing is we are going to create a simple model first, this explicit model, but in a relatively small scale. This is actually a 2D cross-sectional model through a horizontal well screen. We've got 50 meters here. right? And this is something that we can solve very quickly. This maybe 100,000 nodes, if at all, right? And so what we do here is we have a pretty easy model. So this is like 10 meters of hydraulic head around at the borders. We've got 0 meters over here, so it's like a normalized case, test case. And this model will give us a flux, a reference flux. Okay. So in this reference flux we can then use to understand what do we need to do on the large scale as a discretization. So when I think about like a model that I would have to build on regional scale, then I can't afford this discretization. It would rather be something like this discretization. So it will be much coarser. And the boundary condition can only be expressed by a single node, which is not enough to express anything like a screen geometry, like a screen diameter, like a drill bit diameter. But what I can do is, if I find a suitable parameter that gives me an additional resistance there that I can calibrate against the reference model, then that would give me an option to actually have a rule to bring this geometry that I've expressed in the reference model into the large scale model. And that's what we've done here. So what we need to do is we need to make sure that the scale-up model here has the same inflow, has the same flux amount as the reference model, which we deem to be accurate. So what we need to find a resistance parameter. And the resistance parameter could be a transfer rate, if we use this as a leakage boundary condition. Another way what we can use here is actually the node spacing. So for those who have joined the FEFLOW training, we have some chapter there where we show how the inflow into a well changes with different node spacings. And this is actually what we used here. So what we did is we changed the node spacing around this particular node. The bigger the node spacing is, the more influx you get. And then we basically check what is the relationship between the node spacing and the inflow. And then we choose a node spacing that's where the inflow on this coarse discretization matches the explicit model. This looks kind of like this. So this diagram here shows you the inflow into the reference, into the scale-up model, depending on the node spacing in meters. So the bigger my node spacing is here, the more inflow I get. That basically means that if I know what my actual reference inflow is, like 1.6 cubic meters a day in this case, or liter cubic meters a day, then I can basically find the right node spacing for that. And if you then take this combination of a reference model and of a scale-up model, then you can set up different reference models. So what we've done here is we've done different drill diameters, well diameters. And then for each of these well diameters, we have calculated a reference inflow. And from the reference inflow, then an ideal node spacing. So this is all done through inverse modeling. So PEST is a very handy tool there. So we had basically PEST finding the optimal node spacing there. So that's a pretty efficient process to set up this list. And then you've got something like a discretization rule. And this discretization rule you can then apply in a regional model. So even though we are not able to bring in the actual reference diameter into the regional scale model, we can use a coarser discretization, but then use this additional this node spacing rule that we figured out there in order to still have a quite accurate way, representation of the model of the geometry. So to bring an example here, this would be a radial collector well. I think we had that already in another talk. That these horizontal wells that we see there need to be expressed accurately. And what we did is basically we made the study on finding out through this inverse modeling what are the what is the right combination of like lateral node spacing and layer thickness and so on to make sure that this discretization that we find there is the right one. And that's what we implemented here. So when you zoom in, then you see this is like a 1 meter discretization. So it has a fixed mesh. So we can perfectly control the node spacing around these screens. And in this way, we can make sure that we have an accurate inflow there. And finally, coming back to this exercise from the start, if we zoom in here, then we actually use 2 nodes here. So it's a twin tunnel that we have again calibrated against a reference model. And then again, we are also able to handle this pretty complex tunnel structure, including an invert, including spacing of the tunnels and so on, to express it in a regional scale model. So to summarize, we have created a method here to represent geometries and features that are on a local scale model. That we cannot express in a regional scale model through an upscaling parameter into a larger model. This workflow is relatively simple and can be automated, so it doesn't take too much time because we can use PEST as an inverse modeling tool. And this approach is pretty general, so you can use it for horizontal wells, underground mine galleries, mine shafts, surface water features, anything that is like small scale, one-dimensional, lower dimensional, to provide the accurate result there. That's what I want to show you.